Hi everyone. So this is probably yeah, it is. So this is last assignment before your midterms. So in the problem first, so what you have to do in problem first, you have to find null space of the given matrix. So what is the null space of a matrix? So it is denoted by N U double L A. So I'm just writing NA because I'm lazy. So A is some matrix, okay, of any order. Okay, so what it is? So it is all such X. Say A has some order M cross N, okay? So this is all such X in Rn such that AX is 0. That's what null space is. Basically, what you have to do, in other words, this amount to, solving some equations, right? Just equal to B rather than B vector, what we have? 0. Or it has another interpretation also. So, okay, I can tell you that since Sir has defined it. So if you take a map from Rn to Rm, which is linear, okay? Then you have this ker T, which is kernel of T, and how it's defined all such x in the domain such that T of x is 0. I mean, T applied to x is 0. And you might have proved in class that kernel of T is a subspace of what domain? So in fact, if you see this null space is nothing but if you consider this corresponding operator, so it's a m cross n matrix, okay? So when you multiply some x to it, its order is what? N cross 1, right? So it's actually a linear operator from where to where? Rn to Rm. Okay. You can denote, equivalently a matrix. You can, find this corresponding linear operator, and you have shown that this is linear. This was exercise, the very first exercise. So you have this linear map T from Rn to Rm defined like this. Okay. So what is the kernel of T? This is exactly, if you see, null space of A. So in other words, you are computing kernel of this corresponding operator. That's what I wanted to say. So yeah. So what is the A part? So A part is the matrix is given 1, 2, 3, 4. Okay. So basically, like you see, it's amount to solve a system of equations where the coefficients are 0, 0. So you consider this augmented matrix, right? Okay. And this will be equivalent to, let us apply a row operation. Tell me what row operation I should apply. 0. There will be no change in 0 if you see whatever row operation you apply. I mean in this right side of the augmented matrix. So R2 changes to what? R2 minus 3 R1. So if you apply this operation, what you get? Of course, 0 here. And this is 4 minus 3 into 2, that is 6. So minus 2, right? And similarly, if you want to reduce further, but this is also sufficient. So this will imply minus 2x2 if your vector x is x1, x2, and you are looking ax equal to 0, solutions of this. So 2x minus 2x2 is 0. What this implies, guys? This implies x2 is equals to 0. Okay. And from the first one, x1 plus 2x2 is 0. This means x1 is also 0. So what is your null space of this matrix? This matrix has just this vector single 0 or singleton 0 vector. Okay, nice. So similarly, let's do the another part. So what it is, you have given A 1, 2, 3, Let me do the C one, okay? And B is your homework. I mean, it's on the exactly same line, exactly same line. So I think that I can leave for you guys to do. Just, something different. Um, yeah. Oh, actually, it's the same matrix. Sir has, by mistake, I think, retyped that matrix only. Okay, no issues. So 4, 5, 6, 7, 8, 9. I also haven't noticed when he given the assignment. Okay. Okay, so let us again find the null space of this. So you know what you have to do. 1, 4, 7, 2, 5, 8, 3, 6, 9, augmented 0, 0, 0. So this is similar to what operations you will apply. I will not mention. I will of course mention, but you can guess, right? This has to be 0. Such an operation you are gonna apply, right? So you know what you have to do. So 5 minus 4 into 2. So 5 minus 4 into 2, that is 8. 8 minus, right? 4 into 2 is 8. So 8 minus 5 is what, guys? Minus 3. Similarly, 6 minus 4 into 3. So 4 into 3 is 12. So that is minus 6. Similarly here. So this is 0. And what will be the row operation? So 8 minus 7 into 2, that is 14. So if you subtract 8 from 14, I think you get minus 6. And 9 minus 7 into 3. What is 7 into 3, guys? 21, right? And when you subtract 9 from 21, what should you get? I think 12. So this is what you have. Now, you can simplify this further. Which row operation? I leave it to you to judge. So this will be 0, 1, 2, 0, 0, 1, 2, 0. Now this is an interesting problem. So now again I am leaving you to judge the row operation what I am applying. Because that's how you will, you get more practice. So this is pivotal. That is 2, 0, 0, 0, 0, 0. Very nice. So what you get here, guys? X2 plus 2x3 is 0, meaning x2 is minus 2x3, okay? And from the top, x1 plus 2x2 plus 3x3 is 0. Let's substitute x2 here. So what you will get? X1 plus 2 into minus 2x3, right? Plus 3x3 equal to 0. So what is this? X1 minus x3 is 0 if my calculations are right. If not, please correct it. So x1 is equals to x3, right? So what is NA, guys? It is nothing but. So put in place of x1, x3. Everything we are writing in terms of x3, right? Minus 2x3 and what? X3, right? Yeah, such that x3 belongs to R. Now, since you have covered something called span in class, so what is this? This is nothing but span of just this vector, right? 1 minus 2, 1, because x3 you can take common, right? Span of some vectors is basically collection of all linear combinations of those vectors. So here you have just one vector. So this is the complete solution. I hope this is clear. Let me just see one thing in setting in my video. I think I messed up something. It's okay, I cannot, yeah, I'm horrible in technology. Okay, let's do the problem number 2. So, so for that, remember, at least I have done proof in my remedial class on yesterday, Saturday, I have done the proof. And sir might have stated this theorem. So W is a subspace of, you know what, of some, uh, vector space V over some field F if and only if W is non-empty. See, of course, I'm taking this assumption that W is sitting inside V. And number two, what you have to check, x plus y is in W. For every x and y in W, any two vectors, and alpha x is in W for every x in W, and for every alpha in your given field F. So we need to, check whether few things sir has given, whether these are spaces or not. I mean, sorry, subspaces or not. So let us see what we can do. Or, mm, I know an alternative way also which we can do, but let's do this one only. Okay. So, what is A part? W is equals to x, y, z such that x plus y plus z equal to 1. See, whenever no operation is given to you, okay, it is given to you. So, what is given to you? That you are regarding these as subsets of Rn, and Rn you are taking over the field of real numbers. So, that is your vector space. Now, if you remember the definition of subspace, what is the definition of subspace? Definition is a vector subspace is actually a vector space itself, right? Itself with the same operations, right? Same operations as ambient vector space. What do I mean by ambient? Wherever your subset is coming from, whichever vector space. Ambient vector space over the same field, everything is safe. So if it is a vector subspace, so it must have zero, right? Right, it's a subspace. And the zero of the whole vector space is same as zero of the subspace that you might have, observed know, um, while understanding logic behind, this particular result. Okay, so 0, what is 0 here? So 0 comma 0 comma 0. Does it belongs to W? No, right? Because 0 plus 0 plus 0. This is 0 which is not equal to 1. So you don't have additive identity. So it cannot be a vector space at all, right? Because whenever you have these tuples, and if you have this vector addition on Rn, so what is the vector addition on R3 in particular? You add it component wise, and additive identity has to be 0 vector, which is not there in W. So W is not a subspace. Okay, let us do B part. What you have given, W is equals to x, y, z such that x is less than equal y is less than equal z. Now, two property you have to see if this and this is there, right? Something strikes to your mind, it is less than. So example, so let's take some vector 1, comma 2, comma 3. This belongs to W, right? By definition. So if W a subspace, this implies -1 into 1, 2, 3 also must belong to W, right? So, but what it is? -1, -2, -3 belongs to W. What this implies? This belongs to W, meaning -1 is less than equal, -2 is less than equal, -3. This is a contradiction, right? So you see, it doesn't satisfy property. Which property? This closure under scalar multiplication. So this is also not a subspace. So not a subspace. Okay, let us do the C part. What you have given? You have given W is equals to, okay, so x plus 2y plus 3z. You can write it like this also. You can write it as a tuple, comma, any way you want to like to write. But follow a standard way whenever you are doing. 4x plus 5y plus 6z, 7x plus 8y plus 9z. So you have to see if and x, y, z are arbitrary constants, means they are arbitrary real numbers. So you have to see if this is a vector space or not. So I will urge you to verify. So I'm telling you yes. So verify these two properties. What? Um, that u plus v belongs to w. Okay. So how to verify this? Okay, let me verify this. At least this one, huh? So if you have u, so say it is x1 plus 2 y1 plus 3 z1, 4x1 plus 5 y1 plus 6 z1, 7x1 plus 8 y1 plus 9 z1. So arbitrary constant may differ, right? This is how a point look like. And what is v? Some x2 plus 2 y2 plus 3 z2 for x1 plus 5, sorry, x2 plus 5 y2 plus 6 z2, and then 7x1 x2 plus 8 y2 plus 9 z2. So you know how you add two vectors in R3. What is the vector addition? You add them component wise, and you can see it will be of this form. X1 plus x2 plus 2 you can take common, y1 plus y2 plus 3 you can take common, z1 plus z2. Similarly, 4 you can take common, x1 plus x2. 5 you can take common, y1 plus y2. 6 you can take common, z1 plus z2. And 7 you can take common, x1 plus x2. 8 you can take common, y1 plus y2. Plus 9 you can take common, z1 plus z2, right? Yeah, my z I will better write like this small kind of z. Okay. Now, where xi's and yi's are, xi's and yi's are in, and even zi are, right? So, where x1 plus x2, y1 plus y2, z1 plus z2, these are also some constants, right? So, by definition, this also belongs to W. So, similarly, show show that, this also is there. What? Alpha into u is in W for every alpha in R and for every x in W. So this we have chosen U and V be some two, sorry, arbitrary points, right? Okay. I hope you can, verify that. I want to, you know, give you something. Okay, there is another way to prove this, and that is precisely the next problem. So if you observe one thing, this is actually, this I leave to you, or maybe let me do it. So let me copy this thing again. Oh my God, this is hard to, copy. Control plus C, plus V, little bit up. Ah. So observe what is this. So what you can do is you can take, you know, x common, right? If you take x is some constant. If you take x common, what you get? 1, 4, 7. Plus then take y common, right? This is same as this 2, 5, 8. Plus you take the z common. This is same as 3, 6, 9. Where x, y, z belongs to R. So what it is? X, Y, Z are arbitrary. So it is collection of all possible linear combinations of these three vectors, right? Basically, this is span of 1, 4, 7, 2, 5, 8, 3, 6, 9. So if you see, this is a vector subspace. So our conjecture might be span of any collection of vector is a subspace, right? So is it true? That's what we have to, judge. Okay, in the next problem, and in fact, it is true. So, what is the next problem? Problem number, I think, third. So, you have some vectors v1, v2, dot, 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 vn in Rn. Okay, so the question is span of v1, v2, dot, 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 vn necessarily, sorry, necessarily, I forgot the spelling. Let me copy from Sir's question. A subspace of Rn. So, what is the answer? Oh, yes. In fact, I will prove it in more generality and I will ask you to do the same proof. Same proof will hold for Rn. So, let V be a vector space, vector space over some field f, okay? And let us take some vectors v1. Hmm. I think the number of vectors you are taking m doesn't matter. So, and let's take some vectors v1, v2, dot dot dot. Vm belongs to v. So claim, what is our claim? Same, exactly same proof will follow, just replace v by rn and f by r. So what is the claim? Span of this v1, v2, vm, call it something. Shall we call it something? Let us call it S, is a subspace of what? V over F. So that is our claim is. So to see something is subspace, you have to see just three properties, right? One is that it's non-empty. Another is it's what you say uh, it's closed under addition and it's closed under scalar multiplication. Just those three properties. So clearly S is non-empty, right? Because VI's belong to S. Vi is in fact linear combination of V1 up to V1. Now, for example, if you take V1, V1 is 1 into V1 plus 0 into V2 plus dot 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 0 into Vn. Right? Okay. Number 2. So let us take two vectors inside it. So what should we call them? X comma Y belongs to S. So it means X is some linear combination, right? So call it C1X V1 plus C2X V2 dot dot dot. Why I'm writing power X? It means just dependent upon X. It doesn't mean I am multiplying C1 X times. It's just some constant. It is dependent upon X. That's why I'm writing X. So C mx Vm. Similarly, y will be also some form C1y. So you see, rather than choosing scalars like Ci's, Vi's, I have taken dependent upon y. So some scalars because x and y belong to span, meaning they are linear combination of these vectors, right? C2y, V2 plus dot 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 CMy, Vm, where Cix, Ciy belongs to your field for every I in 1 to n. Okay? Now, let us verify together both of the properties and alpha belong to F be arbitrary. So what is x plus y, guys? X plus y is in fact, if you sum it and take the terms together and use the properties of vector space with scalar multiplication and vector addition, how they behave. So C1x plus C1y V1 plus, right? C2x plus C2y V2 dot 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 CMX plus CMY VM. Note that CIX plus CIY belongs to F. I think you remember the definition of field, right? F is a field. So that's what. It is closed under the addition operation. So in fact, this is also a linear combination, right? So this is happening for every I. So this is in fact a linear combination of Vi. So this implies X plus Y also belongs to span of what? We have named it, right? Capital S. Similarly, what is alpha X? Shall I write directly? So alpha into C1X V1 plus dot 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 alpha into CMX VM. Note that alpha, Cix, these all are in F. So F is a field. So this will implies it is also closed under scalar multiplication. Oh, sorry, it is closed under the multiplication operation, right? So because it is a field. So you see, this is also there. So this implies this is again a linear combination of VI's. So alpha x belongs to S. So nothing special about Rn over R. This is in fact true for general vector space that span is always a subspace. So if you see the part C of the above problem, you can also do in this fashion. Oh, it's span of three vectors. Definitely span of some vectors is always a subspace. Okay, very nice. Now, these are like, very beautiful problems. Problem number 4. Okay, So you have to consider two subspaces. Consider two subspaces V and W of Rn. Okay. So you have asked, is intersection necessarily a subspace? Is union necessarily a subspace? Okay. So let us do the A part. In fact, this also you can do in general. I will state it for you in the end, and I will ask you to prove in general. So okay, so let say E is equals to V intersection W. Okay, note 1. If, note 1, since V and W are subspaces, right? This will imply 0 belongs to V intersection W, right? So V intersection W is non-empty, right? You have to see na subspace. If you have to check subspace, you have to check these properties. You remember? Just where I have written the result, yeah. Just these three things you have to check, right? Closure under addition, closure under scalar multiplication, and the that thing. The thing should be non-empty. Okay, so E is non-empty. Okay, good. Now, note 2. Let us verify this other two properties. So let x comma y belongs to E and alpha belongs to F. Oh, sorry. Here I have this real numbers. Okay. Now, so this means, guys, x comma y belongs to V and W both, right? And V and W are subspaces. So what this implies, guys? This implies that x plus y belongs to V, x plus y belongs to W, alpha x belongs to V, alpha x belongs to W. Meaning both of the things are in intersection also. That is what your E is. So by that result, you are done. What? That E is a subspace of Rn. Tell me, have I used anything about Rn here? I just have used the properties of vector space, right? Or vector subspace. So your homework is like in the above I have done. So let V be any vector space over the field F, some field F, and W1, W2 contained in VB subspaces. Take any two subspaces. Show. Same proof, exactly same proof will be there. W1 intersection W2 is a subspace. Okay? Now, let us proceed to the union part. So next, sir is asking, is union necessarily a subspace? So let me tell you, in fact, it's not true. So let me, take some examples. So let's take R3 in particular and define W, say, x comma 0 comma 0. X is in R. So this is a subspace, right? Because this is span of some vector, right? Which vector? 1, 0, 0. Very nice. Let us take W2 to be 0, y, 0. So this is also a subspace. Why? Because this is span of 0, 1, 0. Okay. Now you know what is W1 union W2, right? So call it say U. Note that 1, 0, 0 and 0, 1, 0 belongs to this U, right? But is it there? No, it's not there, right? Because it's not of the form x00 or 0y0, right? So you see, this is the counter example that union of what we get, union of subspaces might not be a subspace. It can be. If you take two subspaces whose union is full vector space, Are Baba, of course, right? So I want to go, little bit beyond your assignment, and I want to tell you one thing. Okay, there is a beautiful thing about union. So let V be a vector space over. So this you can say a mini result over F. Let W1 and W2 be subspaces. Okay, what I want to tell you, when union is subspace, so W1 union W2 is a subspace of V if and only if IFF W1 is sitting inside W2 or W2 is sitting inside W1. This is a very, very, very fantastic result. So it teach you lot of logics of mathematics. So let us do this direction. I mean the converse direction. So let W1 sits inside W2 or W2 sits inside W1. So what this implies, guys? W1 union W2 is what? W2, and or W1 union W2 is what? W1. And in fact, this and this is a subspace, right? Of V is a subspace of V. So this implies W1 union W2 is a subspace. See, this was very easy, right? The converse part. The forward part is so much of fun. So what is the forward part? So let W1 union W2 is a subspace. Okay? To show, what you have to show? W1 is contained in W2 or W2 is contained in W1. Guys, listen one thing. Whenever you have to show P or Q, the strategy is, the logic is, let me write here, to show P or Q, what you do is, let P is true. Let us assume this is true. Okay, done. Fine, very nice. If now let P is not true, assume P is not true and show Q is true. So that means you are done right because you have shown that P is true or Q is true. So that's how the logic works. So for the P and Q statements in mathematics. So let us try to show this fact. So if W1 is contained in W2, we are done, right? Now if W1 is not contained in W2, then what to show? To show this W2 actually sits inside W1. Right? Now how to show this? Okay. So now see what you have given. W1 is not contained in W2, meaning this implies there exists small W2. So W1 is not contained in W2. So there exists small W1 in capital W1 such that this small W1 does not belongs to W2, right? Now what to show? That W1 is contained in W2. So take a point in W2. So to let W2, small w2 belong to capital W2. To show, what you have to show? You have to show W2 is contained in W1. So show that W2 belongs to W1. So if every element of W2 is in W1, you are done. Okay, now note that W2 belongs to W1 and W1 belongs to what? W1 belongs to W2. Okay? What this implies, guys? W2 is in W1. Yeah. W2 is in W2. I'm sorry. That's what I was like. Something wrong I have written. Wait, let me just edit it. Okay, that's what we have to show. Okay, yeah. No. Okay. Just a second. I'm sorry. Yeah. So W1 belongs to W1. W2 belongs to W2. This will implies W1, comma W2 belongs to capital W1 union W2, right? It's an union. And W1 union W2 is a subspace, right? See, that's how we proceed like this. It's so fun. So what this implies? W1, small w1 plus small w2 belongs to W1 union W2. Why? Because this is a subspace. What this implies? W1 W2 is either in W1 or it is in W2. Let us see where it is. Okay, so if W1 plus W2 belongs to W2, what will happen? Let's see. W2 is in W2, right? And it's a subspace, so minus W2 is also there. So it means W1 plus W2 plus minus W2 is also there. Minus W2 is the additive inverse in your vector space definition. So what this implies, guys? W1 belongs to W2. This is not possible. If you see, this is a contradiction. Why? Because is this a contradiction? Yeah. What is the W1? So this implies there exists a W1 in W1 such that W1 does not belongs to W2. So it is contradiction to star, right? Contradiction because of star. Okay, so what this implies, guys, if this is, it has to be in W1 or W2. It's not in W2. So this implies W1 plus W2 is in W1. Now W1 is in W1. So, and W1 is a subspace. So what this implies, guys? Again, by the same logic, W2 belongs to W1. So that's what you have to show, right? See, you have taken W2 in W2, where it is here. You have taken a W2 in W2, this line, if you see. Okay, let me do it by some color. So this you have assumed, this you have to show. In fact, you have shown this, right? Here. So this implies W2 sits inside W1 and done. So you see this kind of small logic. So I always find linear algebra to be the first course where we, properly learn how to write mathematics. So this is about the whole information about the union of two vector subspaces. Okay, now let us proceed to the problem number 5. Okay, so just a notation sir is saying. So if you have a subset of some vector space V, LS we will denote as span of the subset S, basically collection of all possible combinations, in that vectors of the vectors in S. Okay, so let us do something. So what we are asked to do, so A part is let V is equals to R3 and S is equals to 1, 0, 1 and 1, 2, minus 1. Okay, so what you are asked, give a geometric description of LS, span of S. Now guys, to do it, let's understand these vector better. Okay, so what I'm saying is, yeah, what I'm trying to say is let's understand these vectors better as in, so what is LS? LS is all alpha 101 plus beta 1 2 minus 1 such that alpha beta belongs to R, right? Now, the thing is, if you see what exactly it is, right? You have to give the geometric description of this. Just think about, if you have just say, for example, you just have single vector, some v in R3, such that v is non-zero. Say in particular take 1 1 1. So what is alpha v actually? So say this is your, you know, let me draw it. So alpha can be anything, right? So say this is your xy plane, meaning where x-axis and y-axis are, and this is your z-axis. So 1 comma 1 is point somewhere here. So what this alpha v tells, alpha into 0, 2 comma 2 comma 2. So what it is actually alpha v, if I want to plot it by this red color, this is just a line which passes through and goes in the all direction, right? So similarly, you have to understand, for the geometric description of LS. So see, first of all, what all I have in this LS. So let me copy this LS. Where is the, yeah. Oh my God, copying this I always find so difficult. Control plus C. So one vector represents a line in R3, right? Now let us see what the linear combination of two vectors represent in R3. So if you say take beta to be 0, so what LS contains? LS contains the line passing through, you know, um, this all of these, passing, just a second, through 1, 0, 1, right? Similarly, if you take alpha equal to 0, then what is LS? I mean, what LS contains? By above description, LS contains and 0 comma 0 comma 0. Definitely that lines pass through 0 comma 0 comma 0 also. Contains a line passing through 1, 2, minus 1. And of course 0 comma 0 comma 0. So make a line, right? Now, what exactly happens when you take, for example, you have one vector v and you have another vector w. What does this v plus w in your vector calculus represent? So it's the same vector, on some corresponding plane if you take, right? How you add the vectors. So how you add it, like you do this law, no? So this is v, so this is the vector v, and so this is the vector w. So let me write like this. So this actually, you know, you make a something like this, right? And this point denotes the vector v plus w. So what you are doing, you are moving like this. So what you are doing, you have two lines meeting at origin, and when you are adding them, you are somewhere here, and you are taking all possible combination. So what it represent, guys? So it in fact represent a plane, right? So it's a plane. These two vectors represents a plane. Note that. One more thing. Note, which I haven't tell you, but it is important. 1, 0, 1, 1, 2, minus 1. What if 1, 2, minus 1 also you can write in terms of 1, 0, 1? Then it will be a line, right? But you cannot write it. So what is the rank? 1. You make this 0. So 1, 0, 0. This is minus 2, 2, 1. I mean 1. So what is the rank? Rank is 2. So means these two vectors are linearly independent. How to check linearly independent? Two vectors are linearly independent. Just you take alpha 1, 0, 1 plus beta 1, 1, 2, minus 1. This you have to see 0, then alpha beta must be equal to 0. It is here, right? So from this equation, if you consider what you will get, 1, 0, 0, 1, 1, minus 2, 0, 0, 0. That is 2 only, sorry, 2, right? So what you get, 2 beta equal to 0 and alpha plus beta equal to 0, meaning beta equal to 0, alpha equal to, sorry, I did calculation here, beta equal to 0, alpha equal to 0. So in fact, these vectors are linearly independent. Because if say 1, 2, minus 1 depends upon this vector 1, 0, 1, then it will become dependent on that. Then it is just span of a single vector, right? So in that case, it will be a line. So two linearly independent vectors, what they are giving you? They are giving you a plane in R3. I hope this is clear. Okay. So similarly, you have this B part. So what is the B part? Your V is R3 and you have VW in R3, B2 vectors, and say S is VW. Find the set okay. You have to find the set of linear equation which define this S. So say V is some x1, x2, x3 and W is some y1, y2, y3. Okay. So what will be ls, guys? It will be some alpha v plus just a second. Yes, that's what you have to do. So beta w alpha comma beta belongs to R. Right? So what it is, basically you have to find the linear equations which define this particular, you know, object. Yeah, so this is basically alpha x1 plus wy1, alpha x2 plus wy2, and alpha x3 plus wy3. Oh, sorry. Have I written? Oh, I'm sorry. This is not wy3. Sorry. This is what? Beta y1, beta y2, beta y3, where alpha, beta belongs to your real numbers. So similarly, so what you have to do? Basically, I think this I would better explain separately because I don't know how much vector calculus you know. So yeah, this for this question I will put an explanation later on. Later. Yeah, I think that would be better if I have the explanation later on. Explanation later on. Yes. Okay. Now, what is the C part? You have V equal to Rn and you are defining S to be E1, E2 dot 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 Ek, where 1 is less than equal to K is less than equal to N. And what is Ej, guys? Ej is this vector 0, 0 dot 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 0, 1, 0 dot 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 0, where this 1 is on which place? Jth place. So basically E1 would be just 1, 0 dot 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 0, this n tuple. So you have been asked what is L of S. So just it's by definition. So by definition, what is L of S, guys? L of S is collection of all possible linear combination, right? Dot 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 alpha k ek, such that alpha I belongs to R for every I 1 to n. So what it is, guys? If you solve it, you will get alpha 1 0 0 0. Then when you add it with this, you'll get alpha 2, alpha 3 dot 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 alpha k, and then 0 0 dot 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 0. So alpha is belongs to R, where I is in 1 to n. And rest all vectors are 0. So this is what linear span is. You can give actually a more better description, but for that you need to learn linear operators better. So then we will see what is more better description of this. Okay, now the final problem. So what is the final problem? So let V is equals to this Pn. So what is Pn? It is collection of all polynomials of degree less than equal to n. Less than equal to n, okay guys? Have it in mind. It can have less than n degree polynomials also. So where Let us write what is this? AIs belongs to R for every I in 1 to n. So I ask you to show that over R, this is a vector space. And what will be the operations, guys? Let us see. So the operations will be if you take two polynomials, dot 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 a n x n plus b naught dot 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 b n x n. How to add them? Add them coefficient wise. You know that already from your 8th class. It's just now everything we are doing in linear algebra properly. Dot 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 an plus x bn x to the power n. So that is how you define vector addition here. And how you define vector multiplication? That also I think you might have guessed till now. So this is nothing but alpha a naught plus alpha a win plus dot 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 alpha a n x to the power n. That's how you define. Now, what you have asked to describe some things. So first you have to describe linear span of 1 x square plus x and x square plus x plus 1 comma x cube, and then L of x square plus 1 x cube. So first of all we have to describe these. So let us describe the first one. What it would be: a into 1 plus some b into x square, because this is all possible linear combination, right? And that's how you define linear combination, right? A, B, C in R. Solve it a bit. That will be good. So this will be a plus bx square plus bx plus b plus cx cube. Write it in standard form how we write a polynomial. So this is nothing but a plus b. This is the constant term. Say plus b into x plus b into x square plus c into x cube. A, B, C belongs to R. And similarly, what will be this, guys? This will be a into x square plus 1 plus bx cube, ab in R, right? So what is this, guys? A, oh my god, this circle I made. So a plus ax square plus bx cube, a comma b in R. Now the fun question begins now. So what you have to do? You have to check whether these polynomials lie in these sets or not. So what is the first polynomial? First polynomial is x square plus 3x plus 1. So let us see if it belongs to these. So call it maybe L1 and call this maybe L2. So if here plus 3x plus 1 belongs to L1. So if it belongs, what it means? X square plus 3x plus 1 is equals to a plus b plus bx plus bx square plus cx cube. So you should have such a and b. So it means it corresponds to finding, equation. So what it will be, compare the coefficients. A plus b is 1. You know two polynomials are equal if their coefficients are same. So a plus b is 1. What is the next equation? B equal to 3. What is the next equation? B equal to 1. Oh my god. Is this possible really? B is 3 also, B is 1 also. Not possible, right? Because B is a arbitrary constant, but it fixed na in a linear combination. When you take B is fixed, so not possible. So this implies x square plus 3x plus 1 does not belong to your L1. Now let us see if it belongs to your L2. So x square plus 3x plus 1 belongs to L2, meaning x square plus 3x plus 1, you have seen how you have made it. A plus ax square plus bx cube. So this means b is 0, okay, and this implies a is 1 also, and a is, okay, a is 1. No, a is 1, yeah, a is 1. That's what you get from this equation, right? But what about this 3x? So if a is 1, so let's substitute it. 1 equal to x square, 1 plus 1x square plus b is 0, right? This is not same as x square plus 3x plus 1. So again, x square plus 3x plus 1 also does not belong to L2. Do you get it? So you cannot write it as linear combination of those polynomials. So what is your b part? Your polynomial is 10x square minus 11x plus 10. Let us see if it belongs to, L1, what it means. 10x square minus 11x plus 10 is of the form this. What? Cx cube plus bx square plus bx plus a plus b. Compare the coefficients. A plus b has to be 10. Okay. And then b should be 11 from this bx, if you see. Compare minus 11, I mean. And from x square, b has to be 10. Again, not possible, guys. B cannot take two values. So answer is no, it does not belong to span of this. And all polynomials are like that, I think. Okay, let us check if it belongs to span of the other one. So 10x square minus 11x plus 10, let's say it belongs to L2. Then 10x square minus 11x plus 10 is of this form. What form? I actually forgot. Let me see what was it. Yeah, a plus ax square plus bx cube. Ax square plus bx cube. See, anyway, whatever this will be, you can never have 11x, right? Any value you take of a and b. So this is also not possible. So 10x square minus 11x plus 10 does not belong to L2. Okay, what is the C part? That's fine. Ex minus x plus 7, where e is, the natural exponential what you take. So does it belongs to this L1? So it means e to the power x minus x plus 1 should be of this form. What form? Say, let me do it for L2. I will ask you to do it for L1, okay? So it is of this form, ax square plus bx cube. Now, how will you find AB? Here you cannot compare, right? So differentiate both sides. So what you will get? Minus 1 is equals to A will vanish. This will be 2ax plus 3b x square. Okay. Differentiate again. So e to the power x is what, guys? This is 2a plus 6bx. I would say differentiate it again. So what is this? E to the power x is what? 2a is gone, 6b. Oh my god, that's a contradiction, right? Why? Because x is a variable, right? X is not a fixed number. Here you are getting a fixed number. So b you are getting e to the power x by 6, which which is a variable, which is not a number, right? So this implies e to the power x minus x plus 1 does not belongs to L2. Similarly, I request you to show that it also does not belongs to L1. So none of these things, belong. So checking something belong to some span is amount to solve these equations, right? So if the solution exists, yeah, the thing will be in the span. If it does not exist, it will not be in the span. So thank you so much, guys. This is up to, and anyway, I think This part, B part, I asked you to guys, I will not explain. If there is doubt, then I will explain. This is, you can treat as homework. This is not very hard. Okay, thank you very much.